Okay, here we're going to talk about the mass moment of inertia of an object. And this is something that is used in dynamics. And the definition is similar to a mass for linear motion. And it's a body's resistance to angular acceleration, to rotation. Okay, and again, we'll use this in dynamics to help determine the angular acceleration of a body. Okay, so by definition, okay, the mass moment of inertia about an axis is just the integral of r squared dm. Okay, so the further the mass is distributed out from the from the axis, okay, and the larger the mass is, the more the moment of inertia is, the harder it's going to be for angular acceleration to occur. Okay, so the units on this are going to be kilograms meters squared, or slug feet squared. Again, it's mass times distance squared. Okay, again, these units are not very useful, but just remember that the bigger the number, the harder it's going to be to get that body to rotate. Okay, as with the area moment of inertia, we can redefine or recategorize how the moment of inertia is tabulated by using the radius of gyration, where it is simply the square root of the moment of inertia divided by the mass of the object. So if you have the radius of gyration, that's how you can calculate that from the moment of inertia and the mass. Okay, so in solving these through calculus, we'll actually use disks just like we did in centroids. Okay, so the first thing we need to do is figure out the moment of inertia of a disk. So we have a cylinder. Okay, so same thing, it's just a longer disk. Okay, and I'm drawing basically a very thin tube in there. Okay, that's at some arbitrary distance r from the axis, has a thickness of dr given there, and then a height of well, h total. Okay, so here's my equation for the mass moment of inertia. Okay, I altered the mass of my tube here to be just the density times the volume, dv, for my tube. Okay, and then using what I know about the volume, okay, substituting that in, 2 pi r is the circumference. So basically I'm taking the circumference times the thickness dr times the height h, and that's the volume of this thin shell that I have in here. So again, 2 pi r is the circumference times the height times the thickness gives me the volume of that shell. Okay, now integrating from 0 to r, capital R being the radius of my cylinder here, pulling out what's constant, which is 2 pi h times rho. Okay, and I'm just left with r cubed from this r squared and that r. Okay, that gives me rho pi over 2 r to the 4th times h. Okay, rearranging this, I get this. Now inside the parentheses here, this is rho times pi r squared h, which is just the mass of the entire object, of the entire cylinder. So the moment of inertia of a disk or a cylinder is 1/2 mr squared. Okay, so now we're going to use that moment of inertia of a disk to figure out any volume that I have. So like before, we just draw a disk element, okay, figure out its radius, figure out its thickness, okay, so I can find the volume, dv, it's generally going to be pi r squared times the thickness, dz or dy dx, whatever. Okay, then I'm going to go ahead and integrate this, but I'm not going to use this equation up here. I'm going to use, again, my disk. So I find the moment of inertia of my differential element disk, which is 1/2 mr squared, which I just calculated up here, where m is dm, which I can write as rho dv, which is, again, density times the volume of that, which I can put that volume in terms of my coordinates, dz and y or whatever. Okay, and then go ahead and integrate that equation to find I of the entire object. So it's similar to what we've done with centroids. Again, it is just for using this equation right here, okay, to calculate it. Okay, so as before, we can do the composite bodies, okay? Like Inertia, I need to come up with a parallel axis theorem, which again is the moment of inertia about some axis that's parallel to a centroidal axis. So I have a centroidal axis that I'm calling Z prime, and the axis that I'm actually interested in finding the mass moment of inertia about that I'm calling Z. Okay, so I use my equation here. I'm looking at a differential element dm. Okay, and that is actually from my z-axis that I'm interested in is actually d. If I use Pythagorean theorem, that r distance from the axis to dm, okay, is actually d plus x prime squared plus y prime squared. That's what r squared actually equals. So I plug in that for r squared. Okay, then doing basically a FOIL method on this. Okay. I get this. So again, I'm doing, d plus x prime, the whole thing squared, and separating things out. And I get x prime squared plus y prime squared dm, and then 2d x prime dm plus d squared dm. Okay, so it's basically taking all these terms and reordering them in this fashion. Now, x prime squared plus y prime squared, Pythagorean theorem just tells me that's r prime squared for my centroidal axis that I have here. Okay, the integral of x prime dm is just x bar times the integral dm, x bar being the centroid. So if I take the centroid to be x equals 0, basically my centroidal axis here, this middle term will go away. And then finally I just have the integral of dm, which is just m. So this middle term goes away because I'm setting it at the centroidal axis. This first term is just the mass moment of inertia of about the centroidal axis because it's r prime squared dm. So it's the mass moment of inertia about this. This goes away because again I'm using the centroidal, and then I just have md squared. So again, this is very similar to area moments of inertia, just using masses instead of areas. So then, as we've done before, you break up your composite body into simple shapes. You calculate the mass moment of inertia for each part about the reference axis, and then you sum those up, remembering to subtract the whole. So again, very similar to how we've done composite bodies in the past, just using masses, mass moments of inertia to deal with it here.